filter and a 5 kilohertz high pass filter. I want to realize a band pass filter which will pass all frequencies between 5 and 10. So how do I realize this?
Is it by making an all pass filter because it has all the phase difference? It will
No,
pass
I
all.
don't want to make it as a all pass filter. Physically, I am given one low pass filter and one high pass filter. I want to use these two things in a combination so that it becomes a band pass filter.
Um, um,
Yeah, Santita wants to tell something. Anyone else in the class?
So for the band pass
Yeah, just try
filter,
it. Akshay, just try for some time, okay? Just take out a paper and pen and then see how you can figure it out. Sanitha, you can just wait for some time. Let her also try. Actually, I got the question. No? You are just given two filters,
yeah.
and that's again the LCA which is flying around. I want to make a band pass filter out of it.
I don't know. I don't know.
Okay, Sandita, would you like to answer it, or anyone else in the class? Sanjay?
I'm trying, sir. I'll try, sir.
Okay, please.
Sir, I think Sahan has somewhat of an idea because we were discussing this earlier.
Sorry. Yeah.
Uh, no, not. I thought Sahana had an idea about this because we were discussing about this earlier. So,
Uh,
um,
anyone can from the class can tell. Okay, no issues. Got a solution. You just open to the class. Actually, now they have updated the LCA software. Earlier it was cleared for 6G manuals. Now it's cleared for 8G. So these guys are all trying out vertical climbs now.
oh, that's nice. And about this, do we like
Sorry.
have a combination of it by like
Yeah, what I'm telling is you have to combine these two so that you get a band pass.
do we stack it or something? Yes, it is
Sorry.
5 then
You,
10. Stack it or like
how do you want? Okay, let's say these are two boxes. Okay, how do you want to connect these two boxes?
in series.
In series. Okay. So in series means which one wants should come first and which should come the next.
So for band pass, the high filter, high pass filter should come first. For band stop, the low one should come first. Oh no,
No.
yeah, I don't.
Okay. This is telling that you have to connect these two in series. Okay.
mm,
One after another. Series means one after another. Serial bulbs, right? It all gives
mm,
to the serial bulb, same thing. So there is two ways of combining that. One is you connect it in series, okay, one after another, or you can always connect it in parallel.
parallel.
This is called parallel. Your street lights are all in parallel. Just out of curiosity, Akshay, why we can't connect street lights in series?
Because if we switch off one light, all the other lights will also have to be
So
switched off.
if there is a failure at one point, the whole thing gets disconnected.
Mm,
More than that, there will be some load drop and all. But
mm,
basically, that's the reason. But
yeah.
parallel means even if one goes off, the
We
other
can.
street lights can continue. That's what it means, parallel and serial. Okay. So Sandhita told that for band pass filter, we'll have to connect these two filters in series. Now, my question is, which one should come first?
So high pass filter.
Sorry? Yeah, someone wanted to tell me.
So she was saying high pass.
High pass first. Uh, how many of you agree with it? So the other answer obviously is low pass filter
Low
has to
pass.
come first. Okay. So let's say this is a low pass filter and then high pass filter. Let's see what happens. Now this low pass filter will pass frequencies, all the frequencies up to 10
10.
kilohertz because it's low pass.
Mm,
Anything above that, it is going to attenuate. So up to this, I am having a response like this. But my high pass filter will start only at 5 kilohertz. Okay. So, okay, what happened? So 5 kilohertz you start from here. Okay, it will pass anything above 5 kilohertz. So effectively up to 10 kilohertz only you get here, but this fellow will allow things to pass only from 5 kilohertz. So you get the band pass filter characteristics. Is it okay, actually?
yeah.
Now let us see what happens. Now you explain to me how the band stop filter is going to work.
Uh, so it'll be the reverse of this. When we pass the high frequency, I mean the uh,
So this is a high pass filter, okay, and this is low pass filter. So this fellow, how is it going to work? I don't know. If you connect it in parallel, what happens?
um,
I can make one low pass filter which will pass. Now I'll interchange this. Okay, I'll make this as 5. I'll make this as 10. So this low pass filter will pass anything up to 5 and then attenuate all other things. But when it takes this path, it will start from 10 kilohertz
Yeah.
and pass everything else. So effectively what's going to happen is this area you are not going to have anything. So it is stop.
Fine.
Okay. So that's why it is band stop filter. Here you are passing something, so it's called band pass filter. Is it okay, Sangeeta? No? Getting the
Yes,
point?
sir.
Okay. Quite often one gets into a situation because generally band stop and band pass filters are not manufactured. So you'll have to combine these things and then make one yourself. Okay?
Sir, why high pass filter can't be used first in serial series?
For the band pass,
Yes, sir, for band pass.
so you draw it and see no, yourself. My first part of the question was low pass filter was 10 and high pass is, sorry, low pass filter was 10, yeah, 10 and high pass is 5. Then I reversed the filters characteristic itself and then got it. So you try it out. No?
Sir, with
So
low pass being 10 and high pass being 5,
that
while
is possible.
you
But
connect.
my first question was like that. No?
Yes, sir,
Initially, I
pass from,
assumed that. Come again, Suru?
sir, in band pass itself, while
Hmm.
connecting it in series, if you connect high pass filter first and then low pass filter also will give the
Okay.
same.
What Swarup is telling is you connect high pass filter first, then low pass filter. Okay. So what is the characteristics of high pass filter? Where do you want the cutoff to be?
Sir, at 5.
5. So you're telling from 5 it has to go like this, right?
Yes, sir.
Okay. Now I have drawn this. And low pass filter?
Sir, it will cut off from 10. I mean, like about 10 it will cut off. So only up to 10 will be allowed.
Uh, up to 10. It will go up to 10. Okay. Yeah. So it's like this. This is possible. This is also possible. 5 and 10. Okay, now let's see. Is there any catch to it? He says, yeah, possible because what you're telling is correct. It's this fellow will give everything, and yeah, possible. Sarup, it's possible. Either way, it's possible in this case.
Okay, sir.
Yeah. Now, how about this one? Band stop filter. Suppose you retain this as 10 and this one as 5. Okay. Uh, so what happens? 10. So this fellow will pass everything up to 10 and this fellow will pass, high pass will pass after 5. Uh, so you get something like all pass filter then. Isn't it, Sarup?
Yes, sir.
So it will not work in the case of band stop filters. There it
Sir,
has to be.
between 5 to 10, does it get added up or?
No, not added up, it just passes, that's all. It's not an active device, no, so it's not going to add anything. Suppose some power is coming 1 watt in, let us say, 6 kilohertz, it will get distributed equally, that's all. It's not that 1 becomes 1 plus 1. Is that your question?
No, sir. Like before, when like below 5, below 5 or 10 gets added up.
Just
Like,
1 second. I'll just remove everything. Yeah, tell me now. What do you want to connect now? You are talking about band stop or band pass now?
sir, band stop.
Band stop, okay. Let's draw it. Yeah, what is your high pass filter cutoff?
High pass filter is 10.
Okay. Low pass?
5.
5. Okay. So what's going to happen is up to 5, it takes this path, right? It will go like this. And after 10, anything above 10, this fellow is going to take the path. Okay. Now, what's your question?
So the result is like addition of those two paths.
No, that's all.
But when we interchange it and high pass is 5 and low pass is 10.
Now, high pass becomes 5 and this becomes 10. So, high pass is, just one thing, I'll change the color. Yeah. So, what Sarup is telling us now is interchanging this filters. He says from 5 becomes high pass. Sarup, correct? Huh? The green one is high pass now. And the blue one is 10. So what is going to happen is there is no band stop at all. The whole thing gets passed.
Yes, sir. But from 0 to 5, it gets passed one time, and 10 to infinity, it gets one time. But between 5 to 10, does it double?
Okay. Okay. What Sarup is asking is it addition of something? Okay. Filter is not an active device. Not active. Okay. It cannot pump in more energy than what it gets. So what's going to happen is, let us say we are having a frequency of in between, okay? These two, 7.5. Frequency is 7.5 kilohertz. Power is 1 watt. So what's going to happen is this 1 watt is going to come here. It will get evenly distributed to both these things. Yeah, because this is also going to pass, this is also going to pass. So you'll have 0.5 watts coming here and 0.5 watts coming here. It is similar to, suppose you're having a overhead tank, okay, and you're connecting two taps. So water flows, you open both taps, water flows through both the taps. Assuming fully both taps are identical and you're opening both the taps and they're at the same level. Is it okay, Sarup?
Yes, sir. But after, like at the end point, sir, when the wires again get connected.
Uh, so it's again 0.5 plus
So
0.5, no?
single
Again
channel.
becomes 1 watt. So there is no increase in power.
So there's no interference between each other.
Oh, no, no, no. It just passes, that's all.
Okay, sir.
Okay. Assuming that at 7.5 kilohertz, the characteristics are same for both the filters. Getting it? Huh? It should not happen that the characteristics is not. These are all very ideal situations. I told you earlier also. The ideal situation is you have a filter which is exactly like this. But what actually happens is it's going to be something like this. So it should not happen that 7.5 falls somewhere in this region, in this particular region. Then you will have problems. Like what you're telling, it will not be an even distribution of power.
Okay, sir.
Getting it, sir? Huh? Okay. Okay. With that, we have finished filters. Anything you want to ask me on portions, whatever has been covered so far? Saurabh, how is the? I hope you are reading the book also.
No, sir.
You should. Okay. Don't depend on my slides. After I teach something, just go back and have at least a cursory glance because he gives a lot of good and useful information. Okay? Huh? Read slightly more than what is taught. It's always better. Okay. Anyone from the class, any doubts on previous portions what we have covered?
So radiation pattern, sir.
Mm-hmm. Yeah.
Radiation pattern.
Okay.
So that particular part I didn't understand in almost 3/4.
Okay. Even when actually you're suppose you are having a directional antenna. Okay. Non-directional doesn't make any sense because it's just that Meduada type of radiation pattern all wrong. We worried only about radiation pattern of a directional antenna. So if I see this cross section, I cut this three-dimensional figure. Okay. So what's going to happen is it is something like this. In 2D, it's a dish antenna. Let's assume it's a dish antenna. You're going to have a main lobe like this, few side lobes, and maybe some back lobe also. You can't have 100% reflection. So you have main lobe, side lobe. Now, what is this radiation pattern? So what you have to do is, uh, I gave you that how it is actually measured. So you keep your antenna here, then have one receiver at some distance D, and that I told you it should be some thumb rules are there, so that it should not be the near field of the radiation pattern. Now all you have to do is just rotate this antenna about its axis and then keep monitoring what is the power which is coming out. So you plot, so you know that even common sense says that you look directly into a torch, you see the brightest point, right? So the axis, on the axis you see, you will get the maximum power. That is this point. And you are at a distance D. For a distance D, this is the maximum power. Maximum power at distance D. Okay. So you're just both the receiver and let's say the receiver is having a small antenna and it should have a receiver antenna, otherwise it can't receive. It is just both are pointing at each other. Do you agree even that you are going to see the maximum power?
Yes, sir. At same
Okay.
on same line, no, sir.
Orientation. Yes, like just line of sight orientation. Each both the receiver and the transmitting antenna is point. This is transmitting. Okay, you are transmitting from this and using this antenna. Then you're just rotating this antenna about its axis. Let's say the azimuth axis. Okay, then even again, like common sense says that if the antenna points away from you, naturally you're going to see less of the light. So the power level keeps on decreasing for different angles. So what they do is they draw circles. That's a traditional way of representing the radiation pattern, and each circle represents 1 dB down, 1 decibel down. So 1, 2, and this third one becomes 3 dB minus because it is less. Why this minus 3 dB? Minus 3 dB is nothing but 10 log half power is minus 3 dB. That's why minus 3 dB plays a very important role. So your power level has reduced to minus 3 dB at this point. Now there will be some angles where it is absolutely zero, and that becomes the null. So this becomes null. Null means nothing, zero. So you keep doing this for 180 degrees. Generally these antennas are symmetrical. So do this experiment between 0 to 180 degrees at some steps of 10 degrees. Note down the power levels and then make this plot. Then you will get this radiation pattern. Because every time drawing a three-dimensional figure is extremely difficult. So this is one way of representing the radiation pattern. The other one is the Cartesian coordinates. Yeah. If you are not comfortable with this polar coordinates, some manufacturers they give it in form of this Cartesian coordinates. What it means is this 0 corresponds to the uh, it's called the bore site. Okay, bore site comes from rifles. Okay, bore site is the maximum power at same distance d. So this line corresponds to 0 dB, and at some angle it reduces to minus 3 dB. So now you keep plotting this complete thing. So the other side also is going to be symmetrical. Now you draw a line connecting these 2 points and then see where is it intersecting on the angle. So this angle will give the beam width. What beam width? Is the half power beam width, HP beam width. Some manufacturers also give beam width between first nulls. It's not n number of nulls will be there, it's the first null. So you have beam width between first nulls. So don't confuse beam width with bandwidth. Both are different, okay? What is bandwidth? Even for an antenna?
So the exact definition, I don't know, sir.
No, just layman's. What will be for bandwidth? What will be then the x-axis?
Sir, is it wavelength, sir?
Frequency, okay.
Frequency.
Wavelength, frequency. So y-axis, what is it going to be? Anyone from the class?
A voltage standing wave rate.
Yeah, VSWR, correct. Yeah, good. So you say VSWR of 2 is acceptable and then plot your response. Wherever it's intersecting, this becomes the bandwidth. Whereas in beam width, we are talking about angle. Okay. Okay. Even now, is it clear the concept of beam width?
So yes, sir.
Okay. Good. Anything else? Someone wants to ask me something? Of course, this Cartesian coordinates is not given in your reference book. I took it from somewhere else. So you'll generally, if you see any antenna catalog, they'll give one for horizontal beam width, another for vertical uh, beam radiation pattern. Horizontal radiation pattern as well as vertical radiation pattern. Of course, if it's a perfect dish antenna, then there is no issues. But generally, you don't have such antennas. Antennas will be something like in 3D. Let me see whether I can draw it. It will be like a cut cylinder. Okay. So in this case, uh, okay, out of curiosity, I'm asking. Suppose I have an antenna like this. Can you people visualize it? I'm just cutting a hollow cylinder. Cross section wise, it's a half circle. Okay, if you look at cross section in this direction, it's a half circle. But if you look at the entire antenna, it's not a perfect dish. What you people see. How will the radiation patterns be same for horizontal as well as horizontal plane and vertical plane?
I think no.
Sorry?
I don't think it'll be the same. I'm not
Yeah,
sure.
good. Why action?
Uh, because the
Which one?
length
Which
varies
one?
and
Which plane do you think is going to be having a narrow beam width, narrower beam width?
uh, the 2 points of the semicircle, like, you know, in this way,
Uh,
uh, or like corresponding to the plane surface, like up and down will be narrower.
no, let us say this antenna is rotating on this axis. Okay,
Okay.
it's a half sphere, half cylinder which has been cut like this.
Mm. Uh,
So my question is, which plane, the horizontal plane is going to have narrow beam width or vertical
uh,
plane?
I mean, those are the ones.
Yeah, good. Because the length is more, right? If you look at this length is L,
Yeah.
and
Mm.
this one is D, and L is much greater than D. So obviously, this is going to, in the horizontal plane, you're going to have a very narrow beam
Beam.
width, whereas in the vertical plane, you're going to have a broader beam width. Okay. So generally, if you look at antennas, they look like this only. Uh, why? Especially search antennas. I'm not talking about that outer space antennas, just whatever you see in airport. Let's see whether we have some. These are all perfect dishes. Okay, both the L and D is same in this case. Anyone from the class? Why we should have for search antennas a very narrow beam width in the horizontal plane, whereas quite a wide beam width in the vertical plane. Okay, the answer is simple. Okay, see, this is the ground. and you're searching a three-dimensional volume. When you talk about search radars, you're talking about a three-dimensional volume. So what you're planning, what you want is maximum volume. Okay. So you look at the vertical plane, this is how it's going to be. Whereas in the horizontal plane, you can't have such a wide bandwidth. Okay, you are interested in the orientation of the aircraft. So the horizontal plane it will look like this, 2 degrees or 3 degrees, something like this. Whereas in the vertical plane, you are it's okay. Analogous thing is this old hand fans, no pie, which people used to cool themselves by waving it. It's or the flag. Okay, you imagine this to be like a flag. A flag which is rotating about this axis. Its thickness is very less, whereas if you look at the area on the vertical plane, it's quite large. So it just goes around like that. Getting it actually? Yeah. Physical meaning of it. Horizontal plane and vertical plane.
Yes, sir. Yeah.
Okay.
I think this is almost like the TCAS, or the ILS landing antenna.
Ah, ELS,
So,
yeah, okay. There are two different equipments, glide path and horizontal. This thing,
yeah.
localizer, right? So
So,
localizer is going to give it in the horizontal plane and glide path in the vertical plane.
okay.
But then there are two different equipments. Here, what I'm talking is a single transmitter having a radiation pattern whose patterns are different for the horizontal plane and vertical plane.
Okay.
Okay. Anything else? Go through AM concepts. After that, it is going to be digital communication. Today, let me just try to finish this amplitude modulation. The formal definition is instantaneous value of the carrier amplitude changes in accordance with the amplitude variation of the modulating signal. Instantaneous value, that is important, of the carrier amplitude. If it is frequency, it becomes FM. Okay. Otherwise, because we're talking about amplitude, it's amplitude modulation. How that value changes? It changes with the amplitude variation of the modulating signal. That's how you get the amplitude modulation. So, if you look at the time variation of these two signals, this is the modulating signal. This is nothing but your voice. Carrier is having constant amplitude, constant frequency. Okay, this is the carrier. You send these two things into a modulator. What you get is a modulated signal. Is it okay actually? Carrier, modulating signal. These two things goes into a modulator to get the modulated signal. And how this modulated signal looks like is the instantaneous amplitude is in accordance with the peak amplitude of the modulating signal. Wave is called a signal in electronic communication. Okay, so don't think it's something great. It's just a wave. Now this peak of the carrier is VM, capital VM, and carrier is VC. Okay. Using this, we'll define few things. So you have the information or modulating signal which is coming in. So this is voice. This is the high frequency carrier. Okay. So typically 120 megahertz for aviation. Voice, as I told you, is limited to 3 kilohertz. So these two things go into this box called as modulator, and what comes out is a modulated signal. Now looking at the expression of this modulated signal, Akshay, can you just tell me how many frequency components it's going to have?
Oh,
Just the frequency, okay? Don't worry about the amplitude. Just looking at this expression for someone has told you that this is my modulated signal expression. So this one is modulating signal as a frequency F subscript M. Carrier is FC. So they are given you this expression. So can you just make a wild guess how many frequency components it's going to have?
um, 2.
Two. Okay. Anyone from the class?
3, sir.
Three. Good, Sanjay. Why, Sanjay?
It will be the carrier frequency plus the modulating frequency, and the carrier frequency and the carrier frequency minus the modulating frequency.
Why? Good, good. Why? Mathematically?
So mathematically, the second term can be expressed as two terms, sir.
Good, good, good. So it is sine A, sine B, right? Product of sine A, sine B. So you're going to have a plus B term and a minus B term. So as Sanjay is telling, and this of course is going to be the carrier. So if you draw the spectrum, carrier is there FC. So what he was telling is there will be another component FC plus FM and then one FC minus FM. Okay, so you have three frequency components for any modulated amplitude modulated signal. Correct, Sanjay? That's what you wanted to tell me, no?
Yes, sir.
Okay, good. So if you look at it in the time domain, this is how it's going to look like. This dark green things is nothing but the carrier whose amplitude has been changed because of the incoming modulation. So how do you rate or how do you convey to the user what is the performance of this modulating signal? So it's called as modulation index. Okay. Cutoff modulation index. Yeah. And that can be measured by, so suppose you want to see this waveform, you people have all used oscilloscopes, no? In your first year you had some electrical lab. Sanjay, you had seen oscilloscopes, right? Where the time domain plot can be seen.
Yes, sir. It was a very brief one, sir.
Yeah, but you have seen some dabba called as oscilloscopes, right?
Yes, sir.
In which they would have shown you some sine wave running around. So once you get this, you fix a oscilloscope or what is called as maybe in your physics books they would have told you as CRO, cathode ray oscilloscopes or something. You just fix it on, connect this here on the screen. X-axis becomes time and Y-axis becomes amplitude, and then you will see all these waveforms running around here and there. So you can measure this Vmax and V minimum. If you can measure these two things, then you can get the modulation index. Or the other way around is, suppose you know Vm and Vc, which is a mathematical thing. Again, you can get M. So M stands for modulation index, and it can go from 0 to 1. Okay. Uh, that is also possible. Like this V minimum can go all the way up to 0. So you have a 0 here and a 0 here. So M becomes 1. That's also possible. And the other thing is there is no modulation, then this V minimum can go up all the way up to this thing. So M becomes 0. So range is 0 to 1. So as Sanjay was telling, we are going to have three components, FC, FC minus FM, and FC plus FM. Okay. Now this FM it need not be a single frequency, because when you talk about a voice signal, it's not just 3 kilohertz, not just one single sine wave. When I am talking, it is multiple sine waves which are coming out. So it can be not exactly zero, but we assume it to be from 0 to 3 kilohertz. Getting it? So it's a band of frequencies. Okay. So modulating FM is a band which we say it is from 0 to 3 kilohertz for voice. It's definitely it's not going to be zero, something like 20, 30 hertz to 3 kilohertz. But just to make it simple, we say it's up to the 3 kilohertz. And let's assume for time being that FM is the modulating signal is just one frequency, FM. This I'm showing it in the 3 dimension. Okay. So you are seeing it from this. This is your modulated signal. It consists of all these components. One is modulating signal, carrier. The result of modulation is you're going to have FC plus FM and FC minus FM. Even you can see this saffron color, right? It is the frequency is higher than it's greater than FC. But if you look at this blue color thing, the frequency is less than FM is less than FC. So this one is called the upper sideband, and this component is called the lower sideband. That's just a way of telling it. So you have two sidebands and the carrier which is coming out. So why it is a band? Because uh, here they are taking it as 300 hertz to 3000 hertz. Okay. So they make a band, lower sideband and upper sideband. So this is how an amplitude modulated signal is going to look like. So remember this x-axis is frequency, okay, not time. No. And if you look at the power, what we have seen is the voltage waveform. But if you look at the power, so you will have a carrier power, two sidebands power. That becomes the total power. Or you can write this as total power is nothing but carrier power plus power in the lower sideband plus power in the upper sideband. So this is how a power is distributed in a amplitude modulated way. Now, if you look at this expression, this power, actual information, the carrier is not having any information, okay? There's no information in it. Nothing. It's just wastage of power. This lower sideband and upper sideband are carrying the info, but the same info. Both are carrying the information. Carrier has no information. So it's actually a very inefficient way of transmitting information through wireless. But the generation of an AM is much simpler, and it became an aviation standard long time back. So we continue to use this AM only. But otherwise, because of this reason, it's an inefficient way of transmitting. So for other applications other than aviation, there is something called a single side band. So they don't transmit carrier, they don't transmit one of the side bands, they just transmit one single side band, which anyway is going to have the information. So that's how the technology matured. Okay. But aviation, it is normal AM still. Okay, just one last slide. Now we know how the amplitude modulated signal is going to look like. This one is the modulated signal. On the reception side, we have to receive it. So I have this thing coming like this. From the antenna. If I pass it through the diode, what happens, Sanjay? Or I'll make it slightly simpler. If I pass a sine wave into a diode, this is 0. Let's say this is 5 volts and this is minus 5 volts. What will come out of it?
I suppose 1 or 0, sir.
It will pass only the positive portion, right? Positive portion of the wave, the upper part. So it just passes this, so you'll get something like this. Negative part will get attenuated, so you'll get peaks like this. Is it okay? A diode will conduct in only one direction. Okay, the simplest example for diode is you people must be having that sump, no, water tanks below the ground in your houses. You want the water to come only in one direction from the corporation into your sump. You don't want the water to go out from your sump to the corporation line. So what do? You fit what valve do you fit? What is it called? It's called a non-return valve, right? So all inside your sumps, if you see, there will be a non-return valve, so that water should not go back in the reverse direction. So the diode also will conduct only in one direction. So whenever this is positive, then it will allow the waveform to go. So if you apply that analogy here, it just cuts off the negative portion. But my intention is I want to know the envelope. Envelope only is going to give me the information. So I just pass it to a resistor, capacitor network, and the function of the capacitor is it's just going to hold the signal between peaks. So you have peaks here. So, but I wanted to hold this level like this. And the resulting signal is the original information signal. So that's how you retrieve back the information. Okay. Sanjay, is it too complicated or is it okay?
It's okay, sir.
Just go through the book once again. Okay? So you have a modulated signal coming here, modulated, amplitude modulated. What you get is finally the info. This comes out as the information. And that's your aim, right? You're just transmitting information from one place to another. And that's how you get it. Okay, so that ends the amplitude modulation part of it. Next class, we'll start with digital communication. And maybe this weekend, we'll be having a short quiz on what maybe up to amplitude modulation. Okay, Sanjay?
Oh, yeah, okay, sir.
Right. Okay, thanks Sanjay and Akshya. We'll see meet in the next class.
Thank you, sir.